Okay, let's talk about radioactivity. I know, the word itself sounds kind of intense, right? A little scary, maybe. But what if I told you it's actually one of the most fundamental forces in our universe, and that it's happening all around us and even inside us every single second? Well, today, we're going to pull back the curtain and demystify the whole thing. So, to kick things off, I've got a little puzzle for you. What could bananas, the smoke detector hanging on your ceiling, and the stars you see in the night sky, what could they possibly have in common? I mean, they seem completely unrelated, right? But believe it or not, they share this incredibly deep, fundamental connection. And the answer is, they're all naturally radioactive. Yep. Now, hang on. Before you start side-eyeing your fruit bowl, no, your banana is not dangerous. It just goes to show that our usual picture of radioactivity, the one from sci-fi movies or giant power plants, is just a tiny piece of the real story. The truth is, it's a completely natural thing. All right, first up, an invisible natural world. So, if this stuff is everywhere, where does it actually come from? To figure that out, we've got to dive into a world we can't even see. See, radioactivity isn't something humans invented. Not at all. It's a fundamental process, and it really all boils down to one word: stability. Some atoms out there are just naturally unstable. They don't need a push or anything. All by themselves, they just change. And when they do, they release energy. This is happening all the time. In the ground we walk on, in the air we breathe, and yeah, even in tiny, tiny amounts inside of us. Okay, section 2. When an atom decays. To really get what's happening, we need to shrink down. I mean, way, way down. We're going right inside the nucleus of an atom. So you can picture an atom kind of like a mini solar system, right? You've got this dense core in the middle, that's the nucleus, made of protons and neutrons. And then zipping around that core, you have the electrons. For a lot of atoms, this little setup is perfectly balanced, totally stable, no drama. But, and this is the key, not all of them are like that. In some atoms, that nucleus is just unstable. You could say it's a bit wobbly. The forces that are supposed to hold it all together just aren't quite cutting it. It's got too much energy, it's imbalanced, and really, it has one goal in life: let go of that extra energy and find a more stable, calmer state. And that right there is our core definition. Radioactivity is simply the name for that process, an unstable nucleus spontaneously changing, or as scientists say, decaying, to get stable. And as it settles down, it has to get rid of that excess energy and maybe some particles. And that stuff it throws out, that's what we call radiation. Which brings us to section 3, radiation's 3 flavors. So what exactly is this stuff that gets ejected? Well, it turns out this energy doesn't just come in one form. There are a few different types. Let's break down the 3 main flavors of radiation. Okay, so take a look at this. These 3 types are fundamentally different beasts. You've got alpha particles, which are basically beefy little helium nuclei. Then you have beta particles, which are just tiny, super fast electrons. And then there's gamma radiation, which isn't a particle at all. It's pure energy, like a superpowered light wave. Now, check out that quality factor column. Think of it like a damage potential score. Because that heavy alpha particle is like a bowling ball. It dumps all its energy in one tiny spot. That gives it a way higher potential to cause localized damage inside a living thing compared to the others. Moving on to section 4, from Becquerel to Sievert. And this difference between the radiation types, it's not just trivia. It is absolutely crucial, because it directly changes how we measure radioactivity and think about its effects on us. I mean, think about it. We can't see this energy. We can't hear it. We can't feel it. So how in the world do we measure its impact? How do we go from this invisible thing happening inside an atom to a number that actually tells us something meaningful about risk? Well, it turns out it's a 3-step process. First, we measure the activity of the source itself. That's in becquerels, and it's basically just a raw count of how many atoms are decaying every second. Super straightforward. Step 2 is the absorbed dose, measured in grays. This tells us how much of that energy actually gets deposited into a target, say a kilogram of tissue. But that's not the whole picture, right? Because we know different types have different impacts. And that's where the final crucial step comes in. The equivalent dose, measured in sieverts. This is the one that really matters for safety. It takes the absorbed energy and multiplies it by that quality factor we just saw, giving us a real-world measure of potential biological harm. All right, final section, why this knowledge matters. Let's tie all of this together. Why have we been going through all these details about particles and units of measurement? Why is it so important to get this right? So here's the big picture, the main takeaway. Radioactivity isn't some spooky, mysterious force. It's just physics. It's unstable atoms trying to chill out and find stability. The crucial thing to remember is that the radiation they release isn't all the same. An alpha particle is not a gamma wave. They're totally different. And because of that, measuring risk isn't just about how much energy is flying around. It's about what kind of energy it is. That's why we need the Sievert. It's the only measurement that gives us the full story, the real biological picture.
So I'll leave you with this to think about. Knowing that the universe, from the ground beneath your feet to the most distant stars, is in this constant state of atomic change, this dance of decay and transformation, how does that change the way you see the world?